So immediately after I did the grading, I did post a solutions key to our Canvas page. If you've got questions about, well, why didn't you like the answer I gave versus the one you were expecting, please look at that and come talk to me. I am more than willing to discuss what I was thinking as I did the grading and what you were thinking as you wrote the problem and see if we can meet in the middle somewhere. And if there's discrepancy, I'm happy to give points back. I don't know what you were thinking. What I was reading gave me one opinion as compared to the thing I was actually looking at. But that's usually what happens in office hours or in my office or via email. Come talk to me if you've got questions. I want to move on from the visual. We have lots of ways of looking at our data, but I want to do some analysis. And the first idea is to simply describe. Visual descriptions work. Here's a picture with ranges and spread and images, and those are helpful. As we saw from our bar charts, from our histograms, from our scatter plots, those are useful ideas. But my larger overarching goal is to use a statistic from my sample, something I've calculated, or to get a parameter for my population. I'm still trying to describe the same types of ideas that I was describing visually. I'm still looking at center and variability and shape. And we have a lot of different ways to describe these ideas. So on page 97, there's some information from a JD Power result. This file is also in our examples on Canvas. So let's pull this up. This is counting defects per 100 vehicles in manufacturing processes. Based on a whole bunch of information. This is the raw data, these first two columns, that appear on page 97. First of all, should I trust this data? Let's do a digest before we even start looking at making numbers or even drawing graphs or anything else. Is this a reputable source? Blue box tells me the source. Should I trust this?
That says it's for education purposes.
Right, but that's for us. That's why we stole this data so that we could do the educational purpose on this. But should I trust the JD Power company? Does anyone know anything about JD Power? The internet is your friend. Look them up. Who's the JD Power group? JD Power and Associates. Sorry, say that again, Chris.
It says the premier source of benchmark rating is based on independent and unbiased feedback from body.
55 years worth of providing benchmark feedback and data to lots of different industries. They are a well-known and well-respected authority. I'm going to believe this data is accurate. That means I'll take it, this is good data to start with. It's quantitative data, discrete quantitative. It goes from, here's my minimum, to my maximum. So per 100 vehicles examined, I have found between 139 and 265 possible defects within each car. If I was going to make a histogram here to try and figure out what this data looks like, I could sort this data and then create a histogram. We did that Monday or Friday before, I don't remember which. We built histograms. Build me a histogram. What bin size should I use? How wide should I make the groups? We had a rule that told me how wide I should make the groups. It told me how many groups to make, and then I figured out how wide they were. So how many groups should I make? How wide should they be?
I was thinking maybe 20, maybe 25.
Okay, but why? Was that an intuitive guess?
I'm thinking like I'm trying to get like where it's where you can try to see where the midpoint's gonna fall. If you do too many, then it's like very unpredictable, and too little is not enough information.
Okay. Is that enough? Widths of 20s. If I did widths of 20s, I might get enough, but what was my rule?
For the number of beans, so.
It was based on the number, for the number of bits. What was my rule for the number of bits?
We can use 1 plus 3.3 times logarithm of n.
Of how many there are. So that's Sturge's rule. It tells me 1 times 3.3 times the logarithm how many there are. So 1 plus 3.3 times the logarithm of 33 gives me 6. If I'm doing 6 bins, high minus low, 265 minus 139, divide by 6, that tells me the bin width should be 21. 20 sounds like a great number. Nice job, Leo. But I'd like to be able to justify that.
How do I get this chart? I'm trying to have the water.
Okay, so the first thing I need to do is I need to write down bins. So we just said either 21, which would be exactly Sturge's rule, or 20 was your suggestion. And if I'm going to do 20, then I'm going to say, oh, I want these numbers to go from 130 to 270. So I wrote down bins of width 20, right? 130 to 150, 70 to 90. And then I did that histogram through the data analysis tab. So I go to data, over here where it says data analysis, and one of the options is a histogram. Tell it where the data is, tell it where the bins are, and it'll generate this picture. Now, with these pictures, I did 2 different ones on purpose. I did the one with exactly 21, the bins that were requested by Sturge's, and I did one with 20 because sometimes nicer numbers are better. Where's the middle of my data? Where's my center idea? Well, I would say it's somewhere in here or somewhere in here. Hold that thought. The highest class in that version is the one that goes from 150 to 170. The highest class in this version is the one that goes from 183 to 204. So I can say, well, maybe the most frequency is in there. But there's more stuff further to this side than the big cluster on the left. Big cluster on the left, long extension on the right. That makes this data skewed. It makes it one-sided as opposed to being symmetric. And we pick the direction where the long tail is to talk about the skew. So if I want to think about this data, I say to myself, All right, the middle's somewhere here and the long tail is to the right, so it's lopsided off to the right. There's some spread here. It's not all really tightly clustered together. So I've really, from a picture, been able to kind of qualitatively describe these three ideas. I know the middle looks like it's over here. It stretches off to one side. It is kind of spread out, not a lot and not symmetrically, because it spreads out more to the right than it does to the left. But I've got some behavior here. Okay. I want some numbers. What can I calculate to give me some measurement of center? There are lots of options. If I am looking at my factory, I'm producing students, therefore I'm producing grades. I want to know how you all are doing, right? So I give you an assessment, I look at the grades, and I do what with them? What's the thing you are most concerned about in your class scores? When you look at your grades, I heard somebody talking about it right before class started. Sorry? Right, but my final grade, I'm not going to know until the end, right? Or even if I'm looking at last semester, what am I really looking at when I look at my grade report?
The average.
My average. I'm looking at my GPA, right? Average. Okay, wait a minute. Then an average is a measure of center. And our average, also called the arithmetic mean. How do you compute an average?
Everything divided by however many.
Aha. So if I have n items, x1 through xn, then the average adds them up and divides by how many there are. Now, if I'm dealing with a sample, this is the symbol for average. The X with the bar over it, because that's a statistic. It comes from a sample. I'm going to use regular letters, Roman letters. If I'm dealing with a parameter for a population, it's the same calculation. The only thing that changed was the subscript. Instead of using little n from my sample, I used capital N for the whole population. And then we use a Greek letter, mu. Why mu? M for mean. I tend to write this in a slight shorthand because I'm adding up a whole bunch of stuff, right? I tend to use the notation for adding up that I stole from the calculus people. And I'm going to write a capital Greek letter sigma for the word sum. And I need to tell it what I'm going to add up. I'm going to add up all the x's. I should put an index on those, right? So I know which one I'm looking at any given time. I'm looking at x1 or x2 or x3 or x4. I want to add them all up. So I'm going to call these xi, and I'm going to start the counter at 1, and I'm going to end it at n. That means add up, start at 1, go to n. It's a loop in a computer program, right? For I equals 1 to n, do this. And then I have to divide by n. Dividing by n is the same as multiplying by 1 over n. Same formula. I don't care if you ever remember this notation or not, but you'll see that capital Greek sigma to mean sum up frequently. So I wanted to introduce it here. Interestingly enough, there is a physical interpretation for this number. What's the average represent? Let's think of our data all on a number line, like we've done a dot plot. So I'm going to take all of our data and I'm going to put it on the number line. Now, in the example we were just looking at, all of those numbers will be between 139 and 265, and there'll be a bunch of different dots at different places until I get all 33 dots on there, right? I want you to think about each of these little dots as a weight. Like you took a stick and literally put little lead weights at each of those numbers. And now I want you to balance it on the tip of your finger. Like that. Want to be able to let it go and have it stay balanced. But the different weights push down in different places, right? And if there's more weight on one side or if there's weight further out, it's going to push more, right? That's torque. Those of you that have taken a physics class, great. If you've never heard that word, it's the distance times the force we're pushing. In this case, the force is gravity. Like a torque wrench twists a bolt. The balance point, where I put the fulcrum to balance this little teeter-totter, that spot is my average. Every single time. Anybody here on the baseball team? Okay. I want you to take a bat. Put one finger at each end. Bring your fingers together so the bat never strays from being horizontal. What's going to happen? You're not going to be down here by the handle, are you? You're going to be way up here towards the sweet spot on the bat, right? As a matter of fact, if you bring your fingers together, you'll be right at the average of the weight of the bat. And you know exactly where the sweet spot is in that bat. The modern torpedo bat that was just developed last year that broke the home run records is designed to make that sweet spot a little bit bigger so that you can hit better. It's a physical average. And that means that if I take the distance from each point to the average, regardless of whether I do it this way or the other way, if I take this and I add all of these up, that adds up to 0 every time. So this idea is called the deviation, how far we are away from the average. The total deviation must be 0 every time. That's how we find where our average is. By the way, this works in 2 dimensions and 3 dimensions and more. So you can do this with physical objects to find where their center point is, even if they're irregularly balanced. If you go to the airport, there's this big, beautiful hanging sculpture above the top of the escalator when you go up, this big mobile by a guy by the name of Calder. It hangs from a single point. And it stays balanced because they found the average. It's lopsided, really, really interestingly. There's a lot of stuff on one side. They balanced it perfectly from one point by doing this. Okay. What if I go to the JD Power number and I take that 265, that highest data value, and I re-examine a bunch of cars from, let's see, 265 was Chrysler. I go to Chrysler and I do another evaluation of their cars and I find 3,872 defects. What's going to happen to my average if I change that one number, 265, to 3,862? Yes, sir. Matter of fact, it's going to go up quite a bit, isn't it? We can think of taking that one little weight, shoving it way out, and it's going to pull everything down. I'm gonna have to move this fulcrum over to get it to balance again. To that end, this idea of a center is very sensitive to extreme values. If you have a whole bunch of grades in a class, and they're all set, I don't know, your average grade is like a 78. And you've got a bunch of 70s, a bunch of 80s, and a 90, and maybe a 60, and then you get a 2 on something. Isn't that gonna pull your average down? Or you've got a bunch of grades, and then you get 100, it's gonna pull your average up, right? Just that one additional piece can move the average. It might move it quite a lot, or it might move it just a little, depending on how far it is away from the other pieces. So how extreme that value is. Another example. If I asked, what is the average salary in this room? How many of you have a job? Okay, so right now I think the average salary is pretty damn close to 0, isn't it? Unless 2 hands go up. But then I walk in, and I get paid to be here. If there are a bunch of zeros in this room, and I walk in with a salary of $60,000, all of a sudden the average goes way up, doesn't it? One change. Housing in Greensburg. Go across College Avenue, that way, down the hill, across the street, bunch of houses, right? I want to buy a house. I look at those houses, they're all fairly small, right? 2, 3-bedroom houses, small bits of land. Now, go that way instead, across Caritas, out to Mount Thor Road. There's a house on the corner of Mount Thor Road that I believe is 8 bedrooms and 5 bathrooms and sits on about an acre of land and is worth a couple $1,000,000. What's the average house price? Well, that sucker is way out there, isn't it? And it's going to skew, it's going to change where our average is. That's the sensitivity to our extreme. Now, I can calculate this number directly in Excel. If I go back to my JD Power data, I can go here, any cell, and I can write equals average, and then I can say, here's my data. Average number of defects per 100 vehicles is 188.6. You add them all up and divide by how many there were. Piece of cake. And if I change that one number from 265 to 3,862, holy crap, look at what happened. Average went from 188 to 297 just by changing one number. I changed it a lot, but the extreme values have a big effect on my average. Questions? This is not the only available measure of center. I've heard this word before, but not necessarily in reference to math. What's a median on the road?
Middle.
It's that line in the middle, right? It's physically in the middle. So what if I asked, what's the number that's physically in the middle? But if I want to do that, I'm going to line up the numbers first. So I'm going to suggest that we find the number in the middle, but we have to sort our values. Whether we go small to large or large to small doesn't matter. But sort the values and then find the value in the middle. Physically in the middle. That means we'll divide the half that's low from the half that's high. Like the road is divided on the left side and the right side by the stripe down the middle, the median. Perfect. Now, there is a potential problem here. And that depends on how many things are in my list. In the JD Power data, how many things were in the list? It said right at the front of the data pile, right up there, gave me my n value. There are 33. 33 isn't divisible by 2, is it? It's an odd number. So if I want a low half and a high half, the middle is going to be one of my numbers. A short list. I only have 5 things, then the median is the third one. There's a low half and a high half, and that's the middle. That would be on the stripe. Wait a minute, it's the third value, right? Half of 33 is, you have calculators. You do not have to do this crap in your head. Half of 33, 16 and a half. So I would want 16 numbers on the low side and 16 numbers on the high side. That would be 32 numbers and the one in the middle, right? If I round that up, that'd be 17. And that would be the 17th number in the list. I have 5 numbers in this list. Half of 5 is 2.5. Round up to the next number on the list. The other way to think of it is it's in the n plus 1 over 2 position. 33 plus 1 is 34. Half of 34 is 17. It's in the 17th spot. Half of 5 plus 1, half of 6, is 3. It's in the third spot. But if n is already even, then my median is not one of the numbers in my list, potentially. Here's a slightly different list. The problem is that I want my median to divide this list in half. There'll be 3 on the bottom and 3 on the top, right? So the median should be, the stripe in the road should be there. Well, crap. How do I put something between two of my values?
You had the 4 and 6, and then divide them by 2.
Which is our average, isn't it? I take the average of the two numbers on either side. So in our case, the median of this list is 5. But there's no 5 on the list. That's all right. It's still in the same spot. 6 plus 1 over 2. 7 over 2 is 3.5, isn't it? Isn't that in the 3.5 spot? It's between 3 and 4. I can still use this same positional idea. A median is a physical position on my list. Questions? What if I take that bottom number, the 1, and I make it a negative 300? I've changed the number a lot. That would take my median and screw it up. My mean average and screw it up royally, wouldn't it? But what does it do to the median? Nothing at all. If I take that 1 and I make it negative 300, they're still in order, and the physical middle's in exactly the same spot. This is the reverse situation. The median is completely not sensitive to extremes. Which is why you will often see things like home prices, where we have extreme values. Use the median instead of the mean to talk about home prices in a given region. The Greensburg area can say the median home price is, and then give me a number. And I believe that when I looked last semester when I was teaching the math of finance course, the median home price in the city of Greensburg was $285,000. And that means that half the houses are cheaper than that, and half the houses are more expensive. 50%. It divided the list into half. But because we've got palaces out on Mount Thor Road, the average is probably pulled up from that, isn't it? Or if we had a depressed part of the city where houses had basically been abandoned and were vacant, buildings were rotting there, well, then maybe that would pull average down because I have more extremes on the low side than on the high side. Questions? When I looked at my histograms, I don't have a mean or a median marked on here. Again, I can calculate. We worked out the mean up there. If I go back to that cell and change that word from average to median, it'll find the middle. The average is 188. The middle of the list is 185. There we go. But I don't see that down here. The histogram doesn't display, the frequency diagram doesn't display any sort of calculated value. It just gives me the bins, right? And in this frequency distribution up here, I can tell which bin has the most stuff in it. I gave that a name when I talked about it earlier. Earlier today, what did I call that? I wish I'd worn my other t-shirt. a t-shirt that says, everything I say will be on the exam. And I'm like, you're gonna pick a particular word? I'm picking a particular word today. I called it a modal class. The bar that is the highest is the modal class. But that's based on the word mode. And that is another measure of center. The mode is the most frequently appearing value in my data set. When I'm actually just looking at the data, it's a single number. Is there a number that shows up the most? If there is, that's my mode. If there's more than one that's tied for the highest occurring, we had 33 values in our JD Power set. Maybe 2 of them both show up 3 times. Well, then we'd have more than one mode, and we'd call that a bimodal set of data. As a matter of fact, you can have lots of modes, but once you get beyond 2, it's not really useful in a lot of places. This is particularly useful for categorical data. What's the category with the largest number of responses? Are there more than one that are tied? Likert scale behavior. From 1 to 5, how do you like this or hate this? As a matter of fact, for categorical data, mode is usually the only one we get to use. That's why we talked about a modal class. Page 102. I have 2 different piles of data. The heights of 1,000 men, women. If I divide by gender, each data has a clear peak to it, doesn't it? These are frequency polygons rather than histograms. And it looks like men are around 178 centimeters and women 163. But if instead I combine all the data and I don't discriminate by gender or separate my data by gender, I have 2 peaks that are almost the same height here. And that means this is bimodal when I look at it this way. If I had more peaks all at that same height, that would be multimodal data. It's rarely used. We will frequently refer to data as bimodal, but we won't frequently refer to multimodal data. Question. Again, it is possible to compute in Excel directly. But you have to decide whether or not you think there's one or more than one, because the command in Excel changes. If I think there's one, I will type equals mode, and notice it pulls up 2 options for me when I start there. The first one says mode.mult, multiple mode. The second one says .sngl, single. If I think there's only one, I'll type single. If I think there's more than one, I'll type multiple. If there are more than one mode in my data, then when I hit enter, it will spit out a list, not just a single value. There's only one, it'll spit out just one. If there were more than one mode, I would get a cascade of all the things that appeared more than once here. Questions? Mean was 188. Median's 185, mode's 167. Okay. When I described this histogram image, I said it was a skewed histogram. But it turns out that even just looking at our different measures of center allows us to compare those to each other. Bottom of page 102 are three pictures about the same kind of data with three different shapes. The one in the middle is symmetric. It's the same on the left as it is on the right. And if this was a truly perfectly symmetric picture, then the mean and the median would be the same. And it would equal the mode because that's the highest point on that picture, isn't it? This sort of bell curve shape here in the middle is an ideal prototype for a symmetric distribution of our data. But then I've got those two on the outside edges, and they're skewed. And this one here on the left, the long tail goes out to the left. On the right, the long tail goes out to the right. So this is a skewed left set of data, and this is a skewed right sort of data. Don't fall on me. But notice what happens. Because of that tail, that pulls the median above the mean. The mean is sensitive to that tail, so the mean gets pulled down if it's skewed left. If it's skewed right, the mean gets pulled up. So if I look at the mean minus the median, here that's 0. Here that's positive. And here that's negative. So I can actually build my idea of skew by comparing the mean and the median. If the mean is bigger, I should be skewed to the right. If the mean is smaller, I should be skewed to the left. However, the relative size of that skew doesn't really mean it's going to look this distorted when I say, oh, this data is positively skewed. In the J.D. Power example, our average was 188. Our median was 185. The numbers go from 140 to 260. The difference is 3 points. That's not a very big skew, is it? But it does say the data should be skewed. Whether or not that is of practical importance is a matter of both the size of the skew and the importance of the values in the data. Remember, what are we counting in that J.D. Power data? What was the J.D. Power data counting? Number of defects per 100 vehicles. And so saying that we're askew by 3 defects in 100 vehicles isn't a very big change, is it? Again, Excel will generate a skew value. The command is equals skew. And that number will be positive or negative or 0 based on what sort of a tail I have. The utility here is a little less. I want to be able to say which way this is going. But I'm not sure that's enough to really mean something. And that is a question we will be asking a lot throughout this course. I got an answer. What does it mean? Does it tell me something big is happening or something little is happening? Can I really ignore the skew here, or is it something worth looking at? Questions? It is possible in Excel to do lots of these calculations at once. Again, in my data analysis, under data analysis, there's an option for descriptive statistics. And if I click on that and give it the data range, it'll do a whole bunch of these calculations together. Hit OK. And then give it the input range. Boop. Here's where all the input is. The input is in a column. There's a label in the first row, so I should check that. And then it'll do a whole bunch of calculations. I'm going to have it put it in a new worksheet. Oh, I forgot to click on the summary statistics. Go. Top 4 things include mean, median, and mode. There's some other stuff up there. There's a lot more stuff down below. And notice skewness is in there. This data has a skew of 0.76. That's a positive number. Positive skew. I should have a long tail on the right. There are other measures of being askew. There's this thing called kurtosis, which is related to how big the tails are. We'll talk more about that later. You should have heard that term last semester in further data. Range, maximum, minimum. Hey, that's important information. A total, how many there are, a whole bunch of other stuff in here. But I should be able to understand what these mean and what they tell me. Questions so far? There are other measures of center. Mean, median, mode are the most common. But if I work for the federal government, I might actually use a different measure of center, depending on what I'm thinking about. So, for example, another version is called the geometric mean. Okay, wait a minute. I called the average the arithmetic mean. I've heard those terms before, arithmetic and geometric, used in this way. I think they were talking about sequences, series, and things like that. We're talking about growth. When you add stuff, that's arithmetic. When you multiply stuff, that's geometric. So if I have n things, what I'm going to do is I'm going to multiply them all together. And then in averaging, we divided by, what's the opposite of multiplying? In terms of this, I would think of dividing, right? But I already used dividing. If these were all in dollars, I'd have dollars times dollars times dollars to the nth power, right? I don't know what dollars to the nth power are. So I'm going to take a 1 over n power, or I can think of that as an nth root. This is particularly used in growth rates. If I think of something going up by 9% in value and then down by 10% and then up by 12%, if I want to know at the end what happened, I don't add those growth rates, I multiply them. And then I take the root of the appropriate size. In particular, growth rates like this are used in time series data a lot. So you'll see this sort of average in time series. There are 2 other averages we use frequently, but I've just hit the clock, so we'll talk about those next. If you came in late and I still have your homework, please come get it. I have been told that there's potential for weather on Friday. If that happens and my event that is Friday gets canceled, I'm gonna have to rearrange our schedule. We still won't have class Friday. But we may end up with, I give you a video to make up for the missing class because I have to move something the week after or something like that. We'll figure it all out. I will see you all on Monday. Have a wonderful week.